pulse momentum problem, we're going to need to draw a free body diagram, a start MBD, and an end MBD. So we draw this little free body diagram here of said stick. We see it looks something like this. We have the support of our hand right here. We have the force of gravity of the stick. And right here, we have a super big impact force that we're going to go ahead and avoid for the time being. Now for our start MBD, we see that the stick has both velocity about its center of mass as well as rotation about its center of mass. And we're just going to go ahead and assume it's the wrong way. And for the ending, we know that the velocity is the other way. Let's go ahead and put a V1 on there. And we know it's going to be rotating this way about its center of mass. The tracker, we saw that the drumstick, the tip, moved 3/5 of an inch per frame, approximately, and this camera had 240 frames per second. So if we do a little math there, we see that that's equal to 144 inches per second for the initial velocity. And if we go ahead and convert that to feet per second, we go ahead and we get 12 feet per second initially. Inspection of after it hit the pad, we noticed it was going an average of 2/5 inch per frame after looking at the engineering paper. And we know that the camera was operating at 240 frames per second. We go ahead and cancel out the frames here. We're going to get that it's going to be going about 96 inches per second, which is equal to roughly 8 feet per second after we did the conversion. So we have our V initial, we have our V final. We're assuming that angular velocity is roughly 0, being that we just dropped it straight on, very little rotation. We're going to use our equation that E equals the relative velocity of separation over the relative velocity of approach to see that 8 feet per second over 12 feet per second is roughly 0.667. That's our ratio.
Thanks, Kennedy.